So good morning everyone and welcome to this lecture. This is lecture number 3 in wave optics, and if we remember, if I recollect, we were dealing with interference. Do we remember interference? Do we remember interference? Two types of interference we dealt with. The first one was known as constructive interference, when the phase difference between the two waves is n pi, 2 n pi, even multiples of pi. Then we have resultant intensity, which is maximum root over I1 plus root over I2 ka whole square. This type of interference is known as constructive interference. Do we remember it?
Yes, sir.
Then we had the places or points where the interference, the phase difference between them was the odd multiple of pi, and we call it destructive interference. The interference there, the resultant intensity there was root over I1 minus root over I2 ka whole square. Is it clear to everyone?
Yes, sir.
We saw examples of this, and let us now move on to the main heading of this chapter. And the main heading of this chapter is YDSE. What is YDSE?
Young's double slit experiment.
Young's double slit experiment. So let us move on to the Young's double slit experiment, or YDSE. Have you seen what is this YDSE? Young's double slit experiment. Have you seen the arrangement? Let me show you the arrangement of the Young's double slit experiment. What does it consist of, Young double slit experiment? Do you know what are the basic things that are there in a Young's double slit experiment?
Sir, a screen, a source, and
A screen, a source, what? So basically, it consists of a screen, and the screen is the place where you can observe these interference pattern. Now, this interference patterns should be these waves which are interfering on the screen must be coming from coherent sources, and as you can see, S1 and S2 are the two coherent sources, two small slits. You can see the small slits S1 and S2. It is also given that the distance between the slits S1 and S2 is small d. Do you see this?
yes, sir.
The distance of these coherent sources from the screen is always given as capital D. Do you see this capital D?
Yes,
Now these two coherent sources must be coming from a single coherent source, a single source, sorry. Do you see this single source S?
yes, sir.
The single source S is emitting these wavefronts. The single source S is a single slit, is emitting these wavefronts. These wavefronts are getting divided, so this is division of wavefront. Do you understand? And then we have two wavefronts coming, this one and this one, which are coherent, coming from coherent sources. They are going to interfere on the screen, and they are going to form the interference pattern. This point O is the midpoint. Do you see this? This is the midpoint of the two sources. Do you see this?
Yes, sir.
I'll give you a minute to draw this diagram. So what is going to happen here? This is just a description of what happens in a Young double slit experiment. Monochromatic light will fall on the two narrow slits S1 and S2, which are very close to each other, which are acting as coherent sources. These wave or wavefront coming from these two coherent sources are going to create an interference pattern on the screen. alternate bright and dark fringes will be alternate bright and dark bands will be obtained. I will show you those bands. These bands are known as fringes. Bright bands will come where we have constructive interference, and dark bands will come where we have destructive interference. Do we understand this?
Yes, sir.
Constructive interference and destructive interference, and you will get alternate dark and bright bands. I will just show you those bands so that you understand how do you what type of bands you get. The alternate dark, one is dark, the other one is bright. Do you see this? Alternate dark and bright fringes or bands. We have a band which is at the center, and this is a bright band. We call it center maxima. Then you have alternate. The pink ones are your bright bands. In between two bright bands, you have a dark band. Do you see this? So all these green ones are your dark bands. We got this?
Yes, sir.
So this is how you have alternate, bright and dark bands. I'll give you a minute to note it down. This is how these fringes are produced. You don't have to note it down. This is just for you to see and understand. This is a single wavefront. From this single wavefront, we create these two wavefronts, which are daughter or secondary wavefronts, which are coherent. Do we see this? At
Yes.
some points, these two wavefronts are having constructive interference, and at the other points, they are having destructive interference, and that is how you have alternate dark and alternate bright fringes. Do we understand this?
Yes.
Alternate dark and alternate bright fringes you will have, and this is a diagram which gives you the position of all these alternate dark and alternate bright fringes. This chapter is all about understanding. If you understand it well, everything becomes simple. The pink one that you see are bright fringes. Do you see them?
Yes.
So you have bright fringe at the center, then you have bright fringes at the top. The pink ones are your bright fringes. Do we understand this?
Yes.
In between these bright fringes, we have dark fringes. These blue ones in between the bright fringes are the dark fringes. I'll give you a minute to note it down. Now remember these some important points about this, and we will understand them as we go ahead. Central frame is always bright. The central one is always bright. We have this slits. So the fringe pattern obtained due to the slit is more bright than due to a point. If you create points, the fringe pattern will be a lot darker. But if you create slits, because intensity depends on the slit width, the fringes would be more brighter. If the slit widths are unequal, then the intensity would be unequal. If the intensities are unequal, then the dark fringes will not be completely dark and bright fringes will not be very bright. Do we remember this? Yes or no?
Yes.
Now, if you have one slit with red light and blue light, that means they are even if they are coming from coherent sources, but they have different wavelengths, and we will see that variation because of the wavelength. Remember, the slits must be emitting light as coherent sources. The slit must be coherent sources, same wavelength, red and blue, different wavelengths, cannot be coherent sources. Therefore, you will not observe any interference pattern. If the two coherent sources consist of an object and is reflected image, just as in case of a Lloyd's mirror, because of the image getting reflected, it undergoes a phase change of pi. Therefore, everything reverses. The central fringe would be dark and it will not be a bright one. So it will be a dark fringe at the center. It will be just opposite. So center one will be dark and then you will have bright. Do you understand this?
Yes, sir.
I'll give you a minute to note this down. Now the next thing we have to do is to understand how this interference is happening. So what do? We take this center point C, which is the center of the two slits, and we take a point P on the top. The distance of this point, the vertical distance of this point from the central point is xn. Do you see this?
Yes, sir.
Now you have two waves coming and interfering at this point. One is this blue wave or blue wave front, which is coming from the upper slit. One is this yellow wave front, which is coming from the lower slit. The thing that I am going to ask you is, are they traveling the same path?
No, sir.
They are not traveling that same path, and therefore between the blue wave and the yellow wave there would be a path difference. Yes or no?
Yes, sir.
Let me call that path difference as delta x. How much is that path difference between the two waves that are reaching point P? That path difference will be PS2 minus PS1. Yes or no?
Yes.
Now, this is the actual path difference, but now after this, we are going to use a lot of approximation. It is PS2, which is the larger one, minus PS1, which is the smaller one. Now, if this D is very, very large compared to small d, it is very, very far. The distance is very, very large compared to small d. Then you can say what? PS2 minus PS1 can be written as S2L. Do we understand this?
Yes.
So what you have done is, I have drawn a perpendicular from S1 onto PS2. I call that point as L. So I can say that the path difference between the two waves can be written as S2L. Yes or no? And this S2L, which will now become approximately equal to the path difference, can be written as d sine theta. Yes or no? No, d tan theta. Yes or no?
Yes.
Do we understand this?
Yes, sir.
Tan theta or sine theta? D is the hypotenuse. S2L, if you look at this triangle, which triangle I am talking about? If you look at this triangle is what I am talking about. This is S1, this is S2, this is L, this is D, and this is theta, and this is 90. I can write S2L as
D sine theta.
S2L as D sine theta, which becomes my path difference delta x. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
Again, if D is very, very large, capital D is very, very large compared to the small d, we can prove it by simple trigonometry that this angle theta between S2 SL and S2 SL S1L, the angle S2 S1L is equal to angle P OC is equal to angle theta. This will also happen only when the distance is very large. Do you understand this?
Yes, sir.
Also, remember, my path difference delta x is now d sine theta. But again, this is only possible when the distance d is taken very large. We all understand this?
Yes, sir.
Now, if theta is taken very small, now when will theta be small? Again, theta will be small when the distance d is very large. If theta is very small, I can write tan theta will be equivalent to sine theta will be equivalent to theta. Yes or no?
Yes, sir.
So now my part difference delta x, which was actually equal to d sine theta, can now be written as d tan theta. Yes or no?
Yes, sir.
So far so good? So far so good? That means, have you understood up till here?
Yes, sir.
I'll give you 2 minutes to note this down. Now we have reached till the point where we understand that the part difference is d tan theta. Yes or no?
Yes, sir.
Now for constructive interference, what should be the part difference? It should be equal to n lambda. Yes or no?
Yes, sir.
So for constructive interference, I can have the equation d tan theta will be equal to n lambda. We all understand this?
Yes, sir.
That becomes the first thing that we will have to understand here, that for constructive interference d tan theta will be equal to n lambda. Now if you look at the value of tan theta, and to see the value of tan theta, let us go back to this diagram. Looking at this diagram and looking at where the theta is, I will mark theta by this color. Can you tell me what is the value of tan theta? From there,
PC by OC, sir.
tan theta,
PC by OC, sir.
tan theta. Tan theta is this, let me not call it xn, let me call it y. So tan theta will be equal to y divided by capital D. Yes or no?
Yes, sir.
Tan theta will be y divided by capital D. That's it. So now I have d into y by d is equal to n lambda, or the position y will be equal to d n into lambda d by small d. Do we understand this?
Yes, sir.
This will be the y coordinates of the central of the bright fringes. Yes or no? No, yes.
Yes, sir.
N is equal to 0, 1, 2, 3. N is equal to 0 will give you which fringe?
Central maximum.
Central maxima. N is equal to plus 1 will give you upper bright, first bright. N is equal to minus 1 will give you lower bright, and so on. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Yes or no?
Yes, sir.
For destructive interference, we can do the same thing. For destructive interference, part difference will be 2n minus 1 lambda by 2. Yes or no?
Yes, sir.
Let me not write it as n, let me write it as m, so that both become different. Now, we already know that the part difference is d tan theta. D tan theta is 2m minus 1 lambda by 2. I hope all of you understand this.
Yes.
Tan theta value is y by capital D is 2m minus 1. Two m minus 1 lambda by 2. From here also you can find out the position of the mth dark fringe. It will be d. Oh, let me write it in the same pattern. 2m minus 1 by 2 d lambda by small d. Now here we will start m from 1. M will be equal to plus or minus 1, plus or minus 2, and so on. If I put the value of m as plus 1, I will get the first dark fringe upper side. If I put m as minus 1, I will get the first dark fringe on the lower side. Do we understand this?
Yes, sir.
I'll give you a minute to note it down. Sometimes in some question, instead of the slits being vertical like this, where the part difference is d sine theta, they might give you a question where the slits are like this, horizontal. In that case, the part difference becomes d cos theta. When theta increases, your part difference will increase. So I'll just give you a minute to draw this and note this down. The next thing that we are going to understand is fringe width, and it is what it says. It is the distance between two maxima of successive order on one side of the central maxima. You can just call it as the distance between any two successive maxima or any two successive minima. Do we understand this?
Yes, sir.
So if you talk about dark fringe, you find out the position of nth dark fringe. You find out the position of nth bright fringe. You subtract nth dark fringe from nth bright fringe, you will get the fringe width. So you can write the fringe width beta as xn plus 1 minus xn. Do we understand this? When
Yes,
you
sir.
do this, you will get the value of the fringe width as lambda d by small d, and that is a very important result. You can see between the first and the second maxima or first and the second minima, you find out the distance that will be equal to fringe width. Do we see this?
Yes, sir.
Everyone understands this?
Yes, sir.
From all the three diagrams that I have drawn, you don't have to draw the diagram, you just have to understand it. I'll give you a minute to note it down. Then there is one more term which is known as angular fringe width. Angular fringe width is nothing but the angle between two consecutive fringes, and it is nothing but the fringe width beta divided by d. Do you see this? From this diagram, it should be very clear. Yes or no?
Yes, sir.
Fringe width divided by the distance between the source and the screen, that is the fringe width. And you can see this fringe width alpha can be written as lambda by d. It can be beta by d. It can also be written as lambda by small d. I'll give you a minute to note this down. Then we move to the important points about fringe width. One of these points is going to appear in your exam. All fringes are of equal width. The fringe width is lambda capital D by small d, and angular fringe width is beta by d. We all understand this, yes or no?
Yes.
Now, many a times they will give you a question where they will dip this apparatus in some other medium. If you dip this apparatus, or if you carry out Young's double slit experiment in some other medium, what will happen? Your lambda will change. For example, if you are carrying out this experiment in water, lambda in water will be lambda in air divided by mu. Yes or no?
Yes.
So your fringe width will also change. Fringe width is inversely proportional to is directly proportional to mu. Remember, fringe width is directly proportional to lambda. Since lambda changes, the fringe width will also change. Do we understand this?
Yes, sir.
All these points you must remember because they might appear in your exams. It is inversely proportional to the distance. So if you increase the separation beta, the fringe width will decrease. Yes or no?
Yes.
Then you can find out the position of the nth central maxima like this. Yes or no?
Yes.
Similarly, you can find out the position of the minima. You can write it as n or you can write it as m, doesn't matter. Do we understand this?
Yes, sir.
Everybody is able to follow this. All these are important points.
Yes, sir.
One more point. Let me put it here because I think I can put it here. This is a very important question that I have seen. how many fringes will be seen if you change the wavelength of light? So remember, if you see n1 fringes with a wavelength of light lambda 1 in a certain space, we call it field of view, then the number of fringes n2 with a wavelength lambda 2 will be given by this n1 lambda 1 is equal to n2 lambda 2. Everyone has understood this? Yes or no? No, yes.
Yes, sir.
I'll give you a minute to note this down. These are some of the points that you can note down. The distance of nth bright fringe from the mth dark fringe. So you just subtract xn minus xm. Do we understand this? Xn is the position of the nth dark bright fringe, and xm is the position of the mth dark fringe. If you calculate this, you will get this result. I hope you understand what is this. Yes or no?
Yes, sir.
Here we have assumed that n is greater than m. So probably the brighter fringe is away and the darker fringe is on this side. If it is reverse, you just subtract xm minus xn. Do we understand this?
Yes, sir.
Then with increase in the distance between the slit and the screen, angular fringe width of maxima does not change. Fringe width beta will decrease, but the intensity of fringes will decrease. If you go farther and farther, the light will become less and less intense. The angular fringe width does not change. So theta alpha of bright fringe will remain constant, but beta is directly proportional to capital D, so it will increase. The intensity will decrease because if you go farther, the light will become less and less intense. I've told you how does intensity varies with distance. If it is a point source, it is inversely proportional to 1 by d square. Do we remember this?
Yes, sir.
If you have a phase difference of pi, then the central bright fringe becomes dark. That is the case in Lloyd's mirror because one of the sources is coming from a reflected source. There is a phase difference of pi. When two sources interfere in space, the shape of fringes will be hyperbolic. I'll also give you the shape of fringes. If you have pinholes, after this, you can just note it down. If we use pinholes rather than slits, in slits we get bands. If you use pinholes, then the pattern would be just like a hyperbola, and depending on where the screen is placed, you can have different types of fringes that are produced. So you don't have to draw this diagram, you just have to write if you use pinholes, then the interference pattern which we get on our screen is a section of a hyperboloid. Hyperboloid is a is a figure that we get when you revolve a hyperbola. Do we understand this? So if the coherent sources are not coming from slits but they are coming from pinholes, then you will have the image, the interference pattern will be a section of the hyperboloid. Do we understand this? You just write this. It will be a section of hyperboloid, and then you can note down these three cases. If the screen is perpendicular to x-axis, which is the case here in the YZ plane, general cases, then your fringes are hyperbolic. Second case number 2, if the screen is in the xy plane, then again the fringes are hyperbolic. So in two cases, the fringes are hyperbolic. The different one is case number 3. If the screen is perpendicular to y-axis along S1, S2 in the xz plane, then you can have concentric circles. And they might ask you this one. So just remember, when the screen is perpendicular to your y-axis. Y-axis is the axis where your pinholes are made. In the xz plane, you can have concentric circles as well. Do we understand this?
Yes, sir.
Just have to remember the shape. I'll give you 2 minutes to note it down. The next part and the last part of today's class is maximum order. What do I mean when I say maximum order? You can see that we have taken an approximation that the distance d is very large, and tan theta is equal to sine theta. This tan theta is equal to sine theta is only valid when theta is small. If theta becomes large, then it is not valid. Yes or no?
Yes, sir.
If theta is large, it is not valid. It is only valid for small thetas, and therefore for those small thetas, the number of fringes, the maximum number of fringes that you can get for maxima, the maximum number of fringes are d by lambda. The total number of fringes of minima that you are going to get is d by lambda plus half. And do you understand this symbol? This is the symbol of greatest integer. Do you understand this?
Yes, sir.
So the maximum number of maximas or minimas that you can get is known as the maximum order. For constructive interference, the maximum number is d by lambda. For destructive interference, the maximum number of fringes that you can get is d by lambda plus half ka value. Which value we call it? Greatest integer. Here also we have to use the greatest integer. Greatest integer. So it is 1.2, you will take 1. 2.1, you will take 2. Do we understand this?
Yes, sir.
Give you 2 minutes to note it down. Note it down, fatafat. And with this, we will come to an end of today's class. We have seen almost everything regarding theory from YDSE. There is one particular point that is remaining. But first, we will solve some questions up till this part in the next class. And then we will move on and do the last part of this YDSE, which will be shifting of fringes. So we'll do that in the next class. Everyone has noted this down?
Yes, sir.
You are getting time now to go through these formulas, because when you are solving this question, if you have to look at the formula, there is no use, because this question will rely on whether you remember these formulas or not. So I'll see you and we'll solve some question in the next class. Take care. Have a nice day. Bye bye.
Bye, sir.